Okay. All right, so while you're setting up slides, I will just introduce Abhimad Gautam. So Abhimad is a postdoc at UCLA, and he's going to tell us about the deepest photometric constraints on the binary fraction of stars at the Galactic Center.
Here, we'll share, go there, we'll share. View. Full screen, Lynn's got your timer right there.
Okay, great.
That's your pointer right there.
Okay.
Excellent.
Thank you. Hello, everyone. My name is Abhimad Gautam. I'm a postdoc at UCLA, and this project, which is studying the binary fraction of the young stars at the Galactic Center with Photometry. I've done this when working on this project with a lot of folks who are actually in this room. So yeah, this is going to be sharing some new results from this project. So just to start out, there we go. Just to start out with some brief background, AO astrometry and RVs on large ground-based telescopes has revealed a supermassive black hole at the center of the galaxy. And we do this by fitting orbits to the stars that are close to the center of the galaxy near the supermassive black hole. And we find a black hole that has a mass of about 4 million suns, and it's at a distance of 8 kiloparsecs. And I guess one of the things doesn't show up here, but that's okay. But I wanted to highlight the size scale of that orbit. I had a really nice line that was showing you that this is the size scale of this orbit in physical scales. I had a line showing that's about 0.005 parsecs. So this is very, very close. And then once you zoom out, AO on large ground-based telescopes has also allowed us to perform result studies of the star cluster population at the Galactic Center. So we see a population of old stars, which is shown in red in this illustration. And this is making up the nuclear star cluster, which is made up of old, greater than 1 gigayear age stars at the Galactic Center. And this nuclear star cluster has a half-life radius of about 4 parsecs. But then if we zoom in, we see that there's also a population of young stars. So these are stars that are shown in blue in this. And these are concentrated in the central parsec of the Galactic Center. And they have ages on the order of a few mega years, so about 3 to 6 mega years. And we've observed on the order of 10 to the 2 of these OB stars that lets us trace this population. So the work that I'm presenting is specifically studying the stellar population that lives in about the central half parsec of the Galactic Center. So I'm looking for young binary star systems that live in this region of the Galactic Center. And why we want to do this is that we want to understand where these young stars came from. How did they form in this extreme environment? Formation of the young stars so close to the black hole is a difficult process to explain because of the strong tidal forces from the black hole. And the binary fraction is very useful quantity for us to help observationally constrain models that can explain the formation of these stars. So one way the stars may have formed in the Galactic Center is that stars may have formed in an accretion disk that may have existed around the supermassive black hole in the past. And fragmentation may have occurred in this accretion disk, and that would have let you create stars close to the black hole. And one way binary fraction can help you in this is that it can actually constrain the cooling timescales in these models. So for example, in this model by Nakshi et al. 2007, they found that with long cooling timescales in the accretion disk, that would imply a high binary fraction in the top heavy IMF, which the IMF we actually do observationally see evidence of, such as in Liu et al. 2013. And the binary fraction is also important because the binary fraction is affected by dynamical interactions that happen at the center of the galaxy. So there's a very high stellar density at the center of the galaxy, and that ends up reducing interactions between the stars, ends up reducing the fraction of stars that are in binary systems. And then you can also have 3-body interactions with a binary system and the central supermassive black hole that can lead to mergers or evaporations. So this can also end up reducing the binary fraction. And that plot on the right by Stepan et al. 2016 is showing that in about like 6 million years, which is about the age of the young stars of the Galactic Center, you'll end up reducing your binary fraction by about 25–30%. So the binary fraction is very important to observationally constrain for these reasons to both understand the formation of the dynamical processes, but there's hasn't been an observational constraint on the underlying binary fraction at the galactic center. So the way I've been tackling this in my projects has been through a photometric survey. So in Gautam et al. 2019, I presented a variability survey of the galactic center, where we developed new methodology to extract precise photometry from KEK-AO imaging data. And we achieved about 3% precision in this photometric data. And I'm using imaging data taken with KEK-NERC2 of the central about 0.4 parsecs of the galactic center, and both K-band and H-band that's been taken since about 2006 to study the orbits at the center of the galaxy. And in this data set, we have 95 K-band nights, 16 H nights over 16 years. We published a subset of this in Gautam et al. 2019. And in that study, we looked at about 560 stars. And then now we're pushing to fainter stars in this field of view, extending to about almost 800 stars. So among the known young stars that we see in this field of view at the galactic center, we detect, our experiment ends up detecting 3 eclipsing binary systems. So 2 of those that are shown on the left, 16 Southwest and S4258, those were already discovered before. And we identified a new periodic variable in S236, and with more recent Osiris spectroscopy that we've been conducting, we've identified that this is actually another young binary system. And there's some work that we're still working on, but there's some evidence that may suggest that this might be a possibly tidally stripped, there might be a possibly tidally stripped component in this binary system where one of the stars in this system has undergone evolution and has maybe lost its outer envelope. So in the sample, we detect 3 eclipsing binaries. And when we take the eclipsing binary fraction, so this is just calculating what fraction of the stars are in eclipsing binary systems, we find that it's consistent with the local OB binary fractions. So for the local OB stars, it's about 1.6% eclipsing binary fraction. And when we do the eclipsing binary fraction of the known GC young stars, we get 2.9 plus or minus 1.7%. And that would suggest that the underlying binary fraction would be consistent with the local OB binary fraction, which is the underlying OB binary fraction is about 60 to 70% in the local solar neighborhood. But what's something to keep in mind about this number is that this is the eclipsing binary fraction, and that can be biased by things like the temporal sampling of your experiment or your experimental sensitivity that can affect how many eclipsing binaries that you end up actually detecting in your experiment. So in order to get the underlying binary fraction, that requires a lot more work, and it's a little bit more difficult. And so I'm going to be describing how we're approaching this. So determining the intrinsic binary fraction in our experiment has been pretty challenging because it turns out that stars at the galactic center are very variable in our experiment. So this is something we highlighted in our 2019 paper. About half of the stars in our data set are variable over long time scales. And one of the interesting things, so some of the interesting things that we see, so those 2 different stars that are shown on the left side of this plot, the red points are showing K-band photometry, the blue points are showing H-band photometry. And you see these long multi-year dips in a lot of these late curves. So that top one is going through a dip in about 2020, and then the bottom one has several different dips that last for multiple years. And then the 4 right stars that I'm showing, those are more stable, but they still have some fluctuation in the photometry. And all of these different fluctuations and variability in the flux of the stars can mask binary signals that might be existing in there. So we have to account for this underlying variability when we're trying to place constraints on the actual binary fraction. So the way we do this is we generate a mock population of young stellar binaries, and then we simulate this population using parameters for this population that may be typical of a young stellar binary population. I've put some details in there. If you're interested, we can talk more about this later, but I don't have too much time to go into those details here. And then for these young binary population, we generate synthetic light curves of what we expect to be able to, that we would expect to be able to detect in our bandpasses at the galactic center. So like for that top system, that's a very detached system. So you have narrow eclipses, and then once you start pushing stars closer together, you end up getting broader eclipses in phase, maybe some ellipsoidal variability. And then with contact system, you can get these very broad eclipses and variations in the light curve. And then what we do is we take these mock light curves for this stellar population, and then we inject these into our stellar light curves that we have for the galactic center. And what we're trying to do is that once we inject these into our light curves for the actual stars that we're observing, we're trying to figure out our experiment's sensitivity to stellar binaries. So we can ask the question, what fraction of the injected binary signals that we're putting into these light curves can our experiment, once we actually then run these light curves with injected binary signals through our pipeline, what fraction of these can our photometric experiment recover? And that helps us estimate how sensitive our experiment is to be able to detect the types of young stellar binaries that we are looking for at the galactic center. So once we do that, so this is the result that we end up getting, is that when we go through this whole procedure, and this is very preliminary results, so just keep that in mind. These are very new. We want to kind of examine this in more detail. But what we end up finding is that the galactic center young OB star binary fraction ends up being comparable or maybe even higher than the local OB binary fraction. It's very high. So it's 79% plus 14 minus 22. This is that 1 sigma confidence level. And this is just looking at the sample of the about 100 spectroscopically confirmed early type stars at the galactic center. So it's predicting very high binary fraction. And what's also very interesting, just to kind of wrap up, is that when we compare this with other work that's being done by Devin Chu, who's looking at this central stars in the galactic center. So Devin's work is looking at the S stars, which are a group of young stars with very eccentric orbits around the central black hole. He's not detecting any binaries in that sample, and he's placing an upper bound of about 47% in that young S star cluster. And when we look at our constraints of the binary fraction, as we step outside of the S star cluster, further away from the black hole, we end up finding a very high binary fraction. So we are finding a much higher binary fraction outside of the S star cluster. So in this, with using the same types of confidence limits, we can say that the binary fraction outside of the S star cluster is greater than 40%. So this may make sense. So for the S stars, we may expect that they may have gone through a Hills mechanism to be where they are, where a binary system goes close to the black hole, one component gets captured and the other gets ejected. So this would lend credence to that ability to that idea. But we're finding that the binary fraction outside is much higher, more like a typical young OB star type population. So with that, I'm out of time, so I'll leave up my summary and I can take questions. Thank you.
Thank you. Let's see, I don't see any questions on Slack, so are there questions in the room?
Yes, I have 2 hands in the room. Go ahead.
So your model for how the binaries are formed, like you have a tricky disk and then you are forming binary population. So if that model were allowed to evolve over time, you see a change in the binary fraction, and how does that, like, does that indicate, like, your higher binary fraction, does that indicate a certain age for that?
So so the high binary fraction, yes, you can maybe estimate an age. Our constraints aren't the confidence that we're measuring this aren't tight enough to be able to measure an age, because you would expect the binary fraction to lower as you get to an older and older population through dynamical interactions. This is the error bounds on our result aren't precise enough to measure that. But yeah, we're using our other work from Lou et al. 2013 to actually get the ages of what we expect for the ages of the young star at the Galactic Center.
Okay, I had a hand in the back. So go ahead.
Thanks for the nice talk. So I'm trying to understand the recent disk that would form these systems as well. Do you have a sense for how the size of that disk would compare to sizes of typical dusties or in like a unified AGN model? Like how big would that disk be or anything?
So I mean, I'm not as familiar, unfortunately, with these models. I know, like, I mean, a lot of these models do predict like an inner bound edge to the disk that's somewhat seems to be consistent with our observations of about like 0.05 parsecs or so. The outer regions, I'm not sure.
Oh, I think with that, we've got 13 seconds left, so I think we're at time. But
Oh,
we can continue the discussion on Slack.
okay. Thank
So,
you.
Thank you very much.